So in the previous video, we introduced exponential functions, which is the topic for 4.1, and will end up being important all throughout chapter 4. And what we saw with exponential functions is because the variable is up here in the exponent, being able to evaluate these things can be a little bit challenging, and they're really going to test your ability of exponent rules, understanding what it means to raise something to a negative power or fractional power, for example. So what I want to do in this video is just kind of review those facts, review these different rules with exponents. But it's review that I want to do because if you don't have these rules down solid, if you don't have a good foundation with this stuff, exponential functions becomes a much more difficult topic. So when I talk about exponent rules, I'm mostly talking about these three facts right here. Although what we'll see in this video is that these three rules kind of imply three different consequences or three different definitions that I'm going to add on to this before we finish. And there's also lots of variations of these rules, but I don't want to give you a list of like 20 things to know. So I'm going to focus on these three. And I think if we can get solid understanding of these three facts, then that knowledge will imply all the relationships that we need to know. So you're like, all right, so you want me to memorize these three facts? Well, no, not really. I'd more want you to understand these three facts, because if you just memorize them, they're going to get shuffled up and confused at some point. When I'm multiplying together exponents and the base is the same, I add up those different exponents. Oh, that's weird. I would have thought I should multiply those different exponents. There is a case where you multiply the exponents. It's just not this case. This is a case where you add them. Man, this is going to get really hard. Well, it is if it's memorized, but if it's not memorized, if you think about exponents, exponentiation, as repeated multiplication, all of these facts make perfect sense. Thinking about exponents as repeated multiplication only works when the exponent is a positive whole number, but I think that if we can understand it in that case, we can generalize it to the case where A and B are any numbers at all. So what I'm trying to say is this first fact. Rather than memorize this symbolically, think about what you would do if somebody asked you what 2 to the third power times, 2 to the fifth power is equal to. Well, it'd be tempting to call this 2 to the 15th power, but it's not. It's 2 to the 8th power because this rule says you should add up those exponents. Right, but why do I add up those exponents? Well, if you think about this 2 to the third power as 2 times 2 times 2, if you think about 2 to the third power as repeated multiplication, if you think about the exponent as just telling you how many of these 2's you're going to multiply together, well, then we can do the same thing over here for 2 to the fifth power. That would just be 2 times itself 5 times. And so if I'm taking 2 times itself 3 times and multiplying that by 2 times itself 5 times, really all I'm doing is multiplying together 8 2's. 3 of them from this one, 5 of them from this one. If I'm multiplying together 8 2's, I get 2 to the 8th power. That 8 is this 3 plus this 5, but if you kind of picture this 3 as 3 of these 2's and this 5 as 5 of these 2's, then it makes perfect sense that 2 to the third times 2 to the fifth is 2 to the 8th, or more generally, x to the a times x to the b is x to the a plus b. I'm going to give you similar examples to have in mind for 2 and 3 here, and I'm going to go a little bit out of order. What I want to do is talk about 3 next. Suppose I asked you, they don't all have to be 2's, maybe 5 to the third power, and we're raising that to the fourth power, right? This rule says that, I should take this a times this b, this 3 times this 4, and I should get 12. Apparently, this should be 5 to the 12th power. Right, but why is it 5 to the 12th power? Well, if we again exploit the fact that exponents just mean repeated multiplication, then this 4 right here is just telling me to multiply together 4 copies of this thing. This thing happens to be 5 to the third power, but don't worry about the fact that it's kind of a weird thing to begin with. Just think that this 4 up in the exponent is telling me to multiply together 4 copies of this thing. It's hard to write and talk at the same time. But what is this? Well, each of these individual factors here, 5 to the third power, is asking you to multiply 5 by itself 3 times. So all I have is 4 different groups of this 5 times 5 times 5 thing. And what am I doing with those 4 groups? Well, I'm multiplying them together. So all I have is a whole bunch of 5's here. How many 5's do you have? Well, you have 4 groups, and each group has 3 of them. So how many total do you have? Well, you have 12. If you think about what multiplication was when you first learned it way back in the day, if I said that you have, 4 plates of cookies, and on each plate there are 3 cookies, and I asked you how many cookies you had, you'd be like, well, you got 12 cookies, because that's exactly the definition of multiplication. That would be 4 times 3. The same logic works here. When you're raising exponents up to exponents, you multiply together those 2 exponents, and yeah, you can memorize those, but if you have a more tangible example like this in mind, it might make it go better for you. Okay, that's the first and the third rules. What about this second rule here? Well, what the second rule does is it tackles the case where what if the bases are different? What if this is like 2 to the third power times 5 to the third power. Note that the exponents are the same. I'm using the same letter up here. I need either the bases to be the same or the exponents to be the same in order for one of these rules to apply. So we're looking at the case where now the bases are different, but fortunately the exponents are the same. Well, what do? Well, we're going to do the exact same logic that we've done before. We're going to think about exponents as repeated multiplication, in which case this is 2 times 2 times 2, and this is 5 times 5 times 5, and what I'm being asked is to multiply those things together. And you're like, okay, that doesn't really help me. I don't understand how I can rewrite this in a different form. Well, what we're going to do now is we're going to take advantage of the fact that multiplication is commutative. And when I'm multiplying a bunch of things together, I can multiply them in any order that I want. I can take this 2 times this 5 times this 2 times this 5 times this 2 times this 5 if I felt like it. And you're like, okay, I guess you could, but why would you ever feel like it? Well, now what I have are 3 copies of something. 3 copies of 10, it looks like in this case. 3 copies of whatever 2 times 5 is equal to. Wait, 3 copies of something multiplied together? That sounds a whole lot like exponents. It sounds like you're just asking me 2 times 5 to the third power, or 10 to the third power if you want to write it that way. What this rule is trying to tell you is that if you ever have different bases but the same exponent, you can multiply together the 2 bases and raise that product up to the exponent. And that's a lot to memorize if you see it with letters in here. But if you think about a case like this, oh yeah, all I'm going to do is I got 3 2s and I got 3 5s, and I'm going to pair up each of the 2s with one of the 5s, and that will give me 3 copies of 2 times 5, or 10. Yeah, it makes perfect sense that I'd multiply together those bases, and it would still be raised up to whatever the exponent is. 3 in this case. A lot of people at this point are like, yeah, I get it, fine. Well, it's easy enough when it's 2s and 3s and stuff, but what you'll see as the class goes on is it's a lot harder when these are x's or y's or fractions or negative numbers. So again, I really want to stress these fundamentals. It turns out that these 3 rules imply 3 different facts, which I'm going to call consequences of our exponent rules. And these, I'm going to again explain them, give you a way to think about them. But I think if you're going to memorize one or the other, I would understand red and memorize blue. It's totally fine to understand both. But if you're only willing to understand one, understand the red, and you can get away with just memorizing blue. What blue talks about is, what about some special cases? What if we have a base raised up to the 0 power? Or what if we have a base raised up to a negative power? Or what if we have a base raised up to a fractional power? Well, we're going to talk about each of those 3 different cases. For the first one, if we're raising something to the 0 power, the short answer is it's just equal to 1. If you want to be a little bit picky here, this is equal to 1 as long as x is not equal to 0, and 0 to the 0 power is undefined for complicated mathematical reasons that you can kind of ignore. But any other value of x, like 2 or 3 or 5 to the 0 power, negative 10 to the 0 power, whatever, those are all equal to 1. Wait, that's kind of weird. Why would, I don't know, 7, for example, to the 0 power be equal to 1? Think about what would happen if you took 7, for example, to the 0 power and multiplied it by 7 squared. You're like, I don't know what would happen because I don't know what 7 to the 0 power is. I mean, you're claiming it's equal to 1, but this is supposed to be something for me to understand that it's 1. You can't tell me that this is 1 in order to use that for me to understand that this is 1. Right, we're not going to use the fact that this is 1. What we're instead going to do is use this first exponent rule, right? Because what I have is the same base, 7, and I have 2 different exponents, a 0 and a 2. And this first exponent rule up here, which maybe you understand based on this example, tells you that anytime you're multiplying together 2 exponents that have the same base, all you got to do is add up the exponents. So this should be equal to 7 raised up to the power of whatever 0 plus 2 is. 0 plus 2, well, that's just 2, right? Yeah, that's just 2. 0 plus 2 is 2. So 7 to the 0 times 7 to the second power equals 7 to the second power. And you're like, okay, I believe that that's a true equation because I understand exponent rule 1, but how does that help me understand what 7 to the 0 power is? Well, think about what is that thing that you would have to multiply by 7 squared to make 7 squared the answer? What is that thing mathematically that you can multiply by something to not change the value? If it helps to see these as numbers, I'm saying that something here times 49 equals 49. What is that something? Well, that something would have to be equal to 1, right? The only number you could multiply a number by without changing the value of that number would be the number 1. So 7 to the 0 power must be equal to 1. And there's nothing special about 7. You can do this same logic for any base as long as that base is not 0, which is what gives us this first consequence. Moving right along, what if I have negative exponents? Well, what we're going to do is we're going to do an argument really similar to this one. Let's think about 4 to the negative third power. And again, we don't know what 4 to the negative third power is right now, but I want to prove to you what that's equal to by asking you the question, what is 4 to the negative third power times 4 to the third power? And you're like, that's a weird question since I don't know what this is equal to, but kind of see how this is working here. I could use this first exponent rule, even without knowing the value of this thing, to say that since I have the same base, I just want to add up those two exponents. If I add up those two exponents, -3 plus 3 more gives me 0. So 4 to the -3rd, whatever that is, times 4 to the 3rd power is 4 to the 0 power. And as we saw above, 4 to the 0 power is just 1. So what I'm saying is 4 to the -3rd is the thing that I would have to multiply by 4 to the 3rd to be equal to 1. 4 to the -3rd is just the reciprocal of 4 to the 3rd. The thing that I would have to multiply 4 to the 3rd by to make my answer be equal to 1 is 1 over 4 to the 3rd power. That's called the reciprocal of 4 to the 3rd power. If it's easier to see these with numbers in place, 4 times 4 is 16, and 16 times 4 is 64. So what I'm saying is that 4 to the -3rd power is the thing that I would multiply 64 by to make my answer be equal to 1. Well, the thing that I would multiply 64 by to make my answer equal to 1 is 1/64. 1/64 is just 1 over 4 cubed. More generally, x to the -a power is 1 over x to the a power. Anytime you see negative exponents, just think reciprocal. For this third one, it's a little bit harder, but I again want to give you an example, even though most people will probably just end up memorizing the end product here. To understand 3 here, I want to pick on a specific case where the a is the number 1, and then we'll generalize from there. So let's pick, 9 to the 1/2 power, for example. You might already know what this is equal to, but if you didn't know what this were equal to, you would be able to use what we've learned in this video to figure out what 9 to the 1/2 power squared is equal to. Because we saw earlier that our third exponent rule here says when you have exponents raised up to exponents, you multiply those two guys together. So 1/2 times 2 is equal to 1. So 9 to the 1/2 power squared would have to be equal to 9 to the first power, which is just 9. And you're like, okay, but that doesn't tell me what 9 to the 1/2 power is. It tells me what 9 to the 1/2 power squared is equal to. I'd be like, yeah, that's true. But then I can ask you, okay, what did 9 to the 1/2 power have to be equal to so that when I squared that thing, I got 9 as my answer? And maybe you would respond, well, 3 squared equals 9. So I guess 9 to the 1/2 power is equal to 3. And that's entirely true. It's worth pointing out that -3 squared is also equal to 9, but we define 9 to the 1/2 power to be equal to the positive root. Don't worry about that. At any rate, 9 to the 1/2 power is just a number, so that when I square that number, I get 9 as my answer. Another way of saying that is 9 to the 1/2 power is the square root of 9. Similar logic would show that 9 to the 1/3 power would be the number so that when I cubed it, gave me 9 as the answer. And the number that I need to cube to get 9 as the answer would just be the cubed root of 9. Or more generally speaking, 9 raised up to 1 over any number, which I'll use a b to signify, would just be the b root of 9. And that's not quite enough to give us a general statement for what x to the a over b power is equal to. This just tells us what x to the 1 over b power is equal to. But fortunately, the a over b case isn't that much more difficult than this 1 over b case that maybe you understand. What if instead of 9 to the 1/2 power, I had 9 to the, 5/2 power, and I had to figure out what that were equal to? Well, 5/2 is just equal to 1/2 times 5. So I could think about this exponent of 5/2 as 1/2 times 5, and then I could take advantage of this third exponent rule, which says that if you're multiplying together two exponents, that's the same as raising your base to one of those exponents, and then raising that entire thing to the other exponent. So I could rewrite 9 to the 5/2 power as 9 to the 5th power to the 1/2 power. Or if I felt like it, 9 to the 1/2 power to the 5th power. Because in either case, I'm taking 5 times 1/2, and 5 times 1/2 is just equal to this 5/2. And now that we understand what it means to raise something to the 1/2 power, we understand what these two expressions mean. In the first case, I'm taking the square root, because that's what it means to raise something to the 1/2 power, of 9 to the 5th power. So I could rewrite that like this. And in this second case, I'm taking the square root of 9 and I'm raising that to the 5th power. And yeah, the square root of 9 is just 3, but I'm going to leave it as the square root of 9 to really emphasize where all the different pieces of this fraction are going. Generally speaking, anytime you're raising something up to a fractional exponent, the number in the denominator of that fraction will end up being the root that we're talking about. So the second root here, or the b root here, or the third root here. And the number up in the numerator will be the power that's still on your base. And I can either write it in this order or I can write it in this order. What I'm saying is x to the a over b power is the bth root of x to the a power, which is also equal to the bth root of x raised up to the a power. That got a little messy, so I'm gonna throw a box around it. Maybe that makes it better. Hopefully it doesn't make it worse. And I think we now have the minimum written down that you will need for all of the different exponent stuff in our class. There's two more things I want to add, which I suppose you could consider optional, but I think they're worth your time to learn. The first one is kind of a way to tie together this first exponent rule with this second exponent consequence. It's when you're multiplying together two things and they have the same base, and one of those exponents is negative and one of them is positive. If we look up here at this first exponent rule, it doesn't specify that these are positive. That doesn't matter. I just got to add up these two numbers. So a plus negative b. But a plus negative b is the same as a minus b. If I look at this using this second exponent rule, it tells me that I can rewrite x to the negative b as 1 over x to the b power. So I could think about this as x to the a power times 1 over x to the b power. In other words, x to the a divided by x to the b. A lot of books will state this as a new rule, but I think if you have too many rules, then students get confused and they don't understand what's going on and they just try to memorize all of them. So what I think about is if you're multiplying together two exponents and they have the same base, you add the exponents. Oh yeah, that makes sense. I'm thinking about this case. Yeah, and if you're dividing them instead of multiplying them, it's very similar because division as an operation is very similar to multiplication as an operation. All that changes is instead of adding the exponents up, you're going to subtract the two exponents. The reason you subtract them is because really the b that's down in the denominator, you can think about that as x to the negative b, because x to the negative b means the reciprocal of x to the b power. That's what puts it down at the bottom of the fraction here. And then when you have this negative exponent, you're adding together a positive number and a negative number. It's just like you're subtracting those two numbers. The final thing that I'm going to write down here is something that's really similar to Rule 2. Again, some books state this as a new rule, but I just think about it as a special case of this rule that we already have. And much like this second rule, it deals with what if the bases aren't the same? If the bases aren't the same, but the exponents are the same, I saw that I just had to multiply together those two bases and raise that product up to the common exponent. What if the bases are different and instead of multiplying them together, I'm dividing them? Well, you might think that then you could just divide those two bases and raise the whole thing up to whatever the exponent is, right? That would make sense. It looks a lot like this case where I write the exponent one time and I multiply together the two bases because these are being multiplied. So over here, I'd write the exponent one time and I'd divide the two bases because they're being divided. And that's exactly what you do. It makes sense. It's kind of logical. I think about it as a special case of this second exponent rule. A lot of books will write it as a separate rule. Whichever makes more sense to you is totally fine. I guess what you really need for this class is there's 8 facts on here. And if you want to think about them as 8 separate facts and memorize the 8, then fine, you can if you want. 1, 2, 3, 4, 5, 6, 7, and 8. What I would recommend you do is really understand these first 3 right here, and then it's up to you whether you want to understand these 3 or memorize these 3, and then see these additional 2 as just special cases of these 2 that you already understand. I'll leave it up to you what you want to do with these things, but I wanted to at least spend one video reviewing them because I know how important they'll be for the rest of this chapter.